So Sam has set the stage nicely for us in showing us how we can use some of these ray tracing simulations and population synthesis models to try to make predictions for what axion conversion at neutron stars might actually look like. And what I'm going to tell you about now is sort of the second part of this work, which was going and looking for those signals with data. In fact, we're going to use some SETI data, which I think is fun, and why there's a bootleg ET at the top right of my slide. Okay, cool. So I want to start, essentially exactly where Sam left off, looking at some of these plots, which show us the expected signal of axion conversion as a function of frequency. And of course, if we look at these plots, we can see that there are some neutron stars with very broad emission, and there are some neutron stars with much more narrow emission. Broad here meaning on the order of something like 10 to the minus 4 in relative frequency width, whereas narrow meaning something like 10 to the minus 5. So when we ask, like, how do we actually go out and look for these radio signals, we need to do something to estimate our sensitivity. In order to do that, we're just going to use the simple radiometer equation. So basically what the radiometer equation tells you is that your statistical uncertainty on a flux measurement is going to scale inversely with the square root of the product of the frequency width of the signal that you're trying to measure, multiplied by the amount of time you actually spent looking at your source. So this sort of tells us that there are 3 ways to win, right? We can look at bright signals, but the signals, they are what they are. The brightness is set by the axion coupling to photons, which is what we're going to try to figure out in the first place. So we're not going to win by cranking that bright signal up to by increasing the coupling strength. We're just going to get what we get. We could, of course, use very long exposures. So look at places on the sky where there are neutron stars for a really long time. And I would love to do this, and I need all of your help in convincing my radio astronomer colleagues that that's a good use of their telescopes. The other thing we can do is we can go and we can look for these very narrow neutron stars, because if the bandwidth of these signals is quite narrow, it's going to improve our signal sensitivity. So great. What we want to do is look for bright, narrow conversion lines for a long time. Good. Okay. So, and of course, we're in good shape. There are some very narrow neutron stars in these samples that we're generating. But narrow means I need good frequency resolution. And that's actually a pretty hard problem in radio astronomy, because we don't know the mass of the axion, which is to say that we don't know the frequency at which this signal is going to appear. If you look at these plots, all of them are relative to the axion mass. So we need to look at lots and lots of frequencies at very high resolution. And that means we're looking at huge data volumes. Now, the analysis I'm going to tell you about in this work, just the data in what we used as our signal observations was over 500 terabytes. And of course, this is data that's being collected live at radio telescopes. It has to pass through some complicated set of signal processing in order to be rendered in a useful format. And that's just a challenging instrumentation problem. And of course, actually, what I'm saying this in the context of single dish telescopes like the Green Bank telescope. But of course, this is even worse when you're using an instrument like VLA, or maybe in the future, if you're using an instrument like SKA, where you can have tens to thousands of antennas collecting data at gigahertz to tens of gigahertz to 100 gigahertz frequencies. So basically what you have to do is you have to balance a trade-off between bandwidth, so the total bandwidth of your observation, how many frequencies are you sensitive to, and the frequency resolution that you actually have in that observation. But we're very lucky, because this problem of looking for narrow signals is actually the exact same problem that people who look for extraterrestrial intelligence are facing. They're imagining they're looking for ultra narrow spectral lines that you would have if you built a planet-sized radio. Here we're working with, I guess, a neutron star-sized radio with our signal source by axion conversion. So what the Breakthrough Listen project has actually set up is a very, very nice data backend that operates at the Green Bank telescope. And what's really incredible about this backend, which is essentially a GPU cluster that is connected to the telescope for the purposes of processing the data, is that it can handle a 10 gigahertz instantaneous bandwidth. And you should then compare that to how much data actually gets output by any receiver that you would be working with at the Green Bank telescope. And it turns out the most you would ever get is 10 gigahertz. So what this means is that BACKEND can make use of all of the data that's being collected by Green Bank, and it can render it in a format that has both very, very high resolution and also very wide bandwidth. So that's what we're going to use. And we were also fortunate in that the Breakthrough Listen project has actually looked at some really great places in terms of where bright Axion signals might be sourced. So as part of their Galactic Center survey campaign, they looked at the inner galactic center, like the inner few arc minutes, for several hours. So here I'm just showing you on the top, these are sort of, this is the observation plan, you know, what data actually exists. And on the bottom right, you can see like how those observations were actually conducted. So what they do is they point at the very galactic center. That's their A00 field, and that's in the center of this image. And then they actually tile, they do some sort of, not quite mosaicing, but they do different pointings so that they're resolving the inner 4 arc minutes. Now, what you should be comparing this to is the full width half maximum of the beam that GBT is looking in. And essentially, each one of these pointings is separated by a full width half maximum of the beam. Good. So this tells us that we have not only some good data in terms of looking for signals in this A00 region, but we actually have some nice analysis controls in terms of like these C field pointings where we don't expect there to be bright sources and they're sufficiently far away from the A00 field that they wouldn't actually be contaminated by a signal that does appear in the A00 region. Good. So we also have a number of additional control measurements. So as part of this observing campaign, they measured some sort of standard radio flux density calibrators. So 3C295 and 3C286 are sort of the benchmark calibrators that have very well characterized flux density spectrum. They also measured the radio emission at a few different test pulsars. And then we were going to use these measurements as sort of, again, as additional controls. We have a messy environment at the very galactic center in terms of the radio spectrum, and we're going to do our best to get it under control. And when we can't get it under control, we're going to say, well, at least was the data sort of similarly not under control in these auxiliary regions, which of course we know don't contain Axion signals. So on top of that, we actually have to exclude a few of the pointings that were made during this observing campaign. So the first 2 pointings, the ones performed on major Julian date, modified Julian date, 58702 and 58704, those would be great observations to use. Unfortunately, of course, the Earth is moving, and that's going to induce some Doppler shift of narrowband signals that are appearing in our measurements. And that would be a complicated analysis to account for both the Doppler shifting of Earth and also any Doppler shifting that may be due to the orbital motion of neutron stars at the galactic center. So we're just going to exclude those measurements for now. On top of that, we also are going to go ahead and exclude an additional set of measurements that were made on 58734, just because those measurements weren't made with any additional control measurements. And it's going to make it hard for us to tell whether or not we're actually performing a reasonable data analysis on the data collected during that session. I should also note that these this column that's total on-source time, that total on-source time is summing the amount of on-source time for all of these pointings in the within 4 arc minutes of the galactic center, whereas we only care about this very central pointing in the A00 region. So once you've excluded all of the observing sessions that we're not going to be able to make use of, we still have 280 minutes of exposure at extremely high frequency resolutions. This is going to be great for an Axion search. Okay, so the first thing we do, we of course needed to see if our data was like any good at all. So we designed some RFI filters. This is a big background for us because you can see transient spikes of radio power that might mimic an Axion signal if you weren't careful. But we're actually very happy to see that like overall, 85% of our data pass through our acceptance criteria. So we're going to be able to make use of most of those 280 minutes. Okay, but what does the data actually look like? It's not the prettiest. And okay, so one of the costs essentially of this very fancy Breakthrough Listen backend is some strong instrumental effects that are imparted on the data as it's produced by the telescope. So essentially what this backend does is it says, okay, we're collecting data between 4 gigahertz and 8 gigahertz, or C-band observation. And we're going to break that up into 1,300 roughly so-called coarse channels. And then we're going to perform our Fourier transformations of that data on each one of those coarse channels. And that's how we're going to have an efficient signal processing. The problem is on these coarse channels, which are a few megahertz wide, you get these big features. So you can sort of see I have some roll off in my data at the edges of this one coarse channel example, along with some spectral ripples at the top. So actually, the Breakthrough Listen data is like really remarkably resolved. So here in this work, we use the medium resolution data product, which has a native resolution of about 2.8 kilohertz. And that's actually way better resolution than we need for our signals. We need resolution at like 40 kilohertz or 80 kilohertz in order to bandwidth match our expected signals. So what we do is we're going to downbin our data. So in gray, I'm showing you what the data looks like before downbinning, and in black, I'm showing you what it looks like after downbinning to 32 bins at 91.6 kilohertz resolution. And of course, this is going to carry some analysis challenges with it, because although it's like sort of really beautifully resolved at native resolution, these are some big changes from data point to data point, and we're going to need to be careful in how we actually handle that. Also, I should mention that there are error bars on this on these black data points in the Y direction as well as in the X direction. It's just that they're really, really tiny. The errors here are 1 part in 10 to the 4 as compared to the absolute intensity of the signal that's being measured. Okay, so to sort of try to address some of these analysis challenges, we're going to use a tool for non-parametric inference called Gaussian process modeling. So the idea behind Gaussian process modeling is like, let's say you're doing a very, very simple data analysis. The most naive thing you could do is you say, okay, I have data at a location, let's say frequency, and I have the thing that I actually measured. So let's say flux density. And if I was super naive, I could say, fine, all of the errors are uncorrelated. It's an IID Gaussian distribution, or really I'm saying I'm modeling it with a multivariate Gaussian distribution, but the covariance matrix is diagonal. Okay, but like we don't have to do that. We could be a little bit more sophisticated. We could say like, what if I have no idea what shape the data could be taking and what sort of covariances in terms of that shape might be encoded in what I'm measuring? So what we're going to do is we're sort of going to extend this idea of IID Gaussian data to say, let's give the data some covariance, and let's prescribe what form that covariance should take. And we're going to prescribe it in a way that tells us something that uses the information that we know about the actual data. Okay, so what does that actually mean? So let's say I was looking at this. This is not radio data. This is just some fake data I mocked up. And what I did is I drew data from this true model in black, which is just sinusoidally varying along the x-axis. And so we have some shape, and then we have statistical errors on top of that shape. And now let's say I was very simple and I had never heard of a sine function before, and I wanted to figure out how would I actually analyze this data. But if I wanted to look at, say, a bump in this, I can't see my own mouse. If I wanted to look for a bump in this data at 8, I mean, I would be stuck, except now Gaussian process modeling is going to help me. What I'm going to say is that all of this data, it actually has a covariance, and the scale of the covariance, sort of in terms of the overall fluctuations up and down, is going to be set by what am I actually seeing in the data. And similarly, there's going to be a spatial scale. So like 2 points in the data, how correlated are they by this covariance matrix? That's just going to be another hyperparameter. And I'm going to want to tune it so that it matches what I'm actually seeing happening, and will allow me to get a good description of the data. But of course, the point here is that I'm only talking about covariances. I'm not actually talking about like the mean of the distribution. So what shape the data actually looks like. So the point here is just by saying, I'm going to allow my covariance matrix to take this form, I can then work backwards and make an estimate of what the model was that this data was actually drawn from. Okay, so I did this on this example with like a super simple Gaussian process model. So he's the simplest possible covariance kernel. So it's an exponential squared kernel that's set. So the correlation between 2 points scales like the exponential square of the distance between them. And so I've used this as part of a search for a bump at about 8. And what I'm showing you here is I didn't put any model assumptions in except for what the shape of the bump I wanted to look at was. And my Gaussian process model is able to make a pretty accurate reconstruction of what the true model that the data was drawn from, along with I can add my signal model on top of that and ask, like, how well does that actually fit the data, and what does that mean statistically? So I'm just comparing this. In red, you have your signal model that's fit to the data, and black, you have the null model that's fit to the data. So this is great. It's a super flexible tool, and it's one I really like using. But of course, you have to be a little bit careful with it, because what you're really doing here is you're adding contributions to the covariance matrix on top of that, the diagonal component that's coming from just normal sampling error of your data. So you're adding covariance. That means that you're sort of weakening your ability to detect an actual signal, but oftentimes this is worth it when it comes to actually developing a good model fit to the data. Cool. So we're going to use that for the data we have here. But we're going to be a little more sophisticated than what I've been talking about. We're going to try to leverage the information that we do understand about the shape that this data takes. And for what we don't understand, we're just going to say, okay, hit it with a Gaussian process model. So what you see here is you have the symmetric exponential squared roll-off at the edges, and you also have these spectral ripples. Now, I don't really know how to accurately model in a parametric way these spectral ripples. So I'm going to just say, forget it. That's for the Gaussian process model. But for the exponential squared roll-off, I do know what e to the minus x squared, I know how to code that, right? So we're going to combine a parametric model, so for the roll-off, with the non-parametric model, the Gaussian process model, that is going to describe these ripples, and is also going to have an additional component in it that is going to let us address other sort of astrophysical or instrumental mismodeling that we just might not have known about in the first place. So the way we do that is we're going to use a quasi-periodic exponential sine squared kernel that's going to model the spectral ripples, and then a stationary exponential squared kernel is just going to take care of the other non-periodic mismodeling for us. Now the point here is when I choose my covariance matrix, or when I choose my Gaussian process model kernels, they always have a length scale again. It's telling me how correlated are any two data points. And the point is that I'm going to choose that length scale such that it is always larger than the signal that I actually want to go look for. That way, my Gaussian process model can't fake a signal. It doesn't have the flexibility to produce a single frequency bin excess because the data are too correlated. And that's, of course, what our signal is going to look like, just a single bin frequency excess. Okay, so what does this actually look like? I mean, there's some, you can push this through a likelihood analysis framework, but I think the plot above is more informative. So what I've done here is I've taken my parametric model, I've combined it with my Gaussian process model. So our data points with their super tiny error bars are in gray, and the parametric model that I fit is in red. So that has that roll off, but it's flat at the top. And then, of course, that's not a very good description of the data. So the Gaussian process model takes over, and you can see in blue the Gaussian process model fit to essentially the residuals after taking data and subtracting off the parametric model. And the combined fit is shown in black, and you can see it's very, very good. So that's exactly what we wanted to see. We're able to develop a good fit here. Now, I've already been talking about a parametric model for the background. So if we want to go look for a signal, it's very easy. We're just going to add one more component to that parametric model, and that's just going to be a single frequency bin excess. That's what our signal looks like. So once you've done that, you can use standard frequentist techniques to compute detection test statistics and place up upper limits and so on. It's all relatively straightforward. I do think it's interesting that this is a calculation that it's sort of a hybrid Bayesian frequentist calculation. In fact, when you work with a Gaussian process model, you're working with a marginal likelihood. But now we want to set frequentist, talk about frequentist quantities. So it's a little odd, but it turns out it works. There are some nice papers by Kyle Cranmer and some of his collaborators on sort of the theory of applying this marginal likelihood in a frequentist manner, along with a different applications my collaborators and I made of this modeling technique in X-ray data. Okay, cool. So I will assume that you trust me that this analysis can be done. And when we go and look at what can we actually extract from the data in terms of setting limits or trying to make a detection of an excess, this is what the analysis product of from a single coarse channel looks like. And of course, we're going to end up doing this 1,300 times to cover the full 4 to 8 gigahertz bandwidth. So on the top, what you see is the flux density limits that we're able to place by analyzing this data. And on the bottom, you see the detection significance. So you can think of this number in terms of sigma. Do I see any 3 or 4 or 5 sigma excesses in this coarse channel? No, I don't. And I'm able to place some constraints at the level of about 5 millijansky on excess flux density that appears with a signal width of 91.6 kilohertz. Okay, but it is always important to validate these things. I mean, it would be very sad to build an analysis and reduce data and apply it to all the data, only for it to not actually be able to discover a signal or place robust limits. So here, what I'm showing you is just some robustness tests of this framework that we've constructed. So what I've done here is I've taken one of these spectra that Sam generated, downbended it to the frequency resolution at which we performed the analysis, and then just injected it on top of real data. And I'm making sure that when I inject the excess in real data, that I can actually recover it. So the top plot is showing you, and these are all sort of arbitrary flux density units. You shouldn't think too hard about the y-axis on this top plot. The top plot shows you what the data looks like. That's gray. In black, you have the null model fit. So what we would have fit to the data had we not injected any signals. And the red shows you what that injected signal template actually looks like. And you can see that there are other neutron stars that are contributing to the flux density that we see on this coarse channel, but we're overall going to be dominated by this one single bin excess just to the left of 6,000 megahertz. Now, the bottom 2 plots, what you can see are just first, what do we get in terms of if I inject a signal with some particular flux density, what is the flux density that I reconstruct as the magnitude of that excess? The gray dotted line is the injected signal strength. The black is the signal strength that we recover from our analysis. And the red is the 95% upper limit. And you can see that within the air bands for that 95% upper limit, that's in green and yellow, we're setting appropriate upper limits. They're not excluding real signals that are present in the data. Eventually, as the signal becomes very strong, as we'd expect, the magnitude of that signal is accurately reconstructed. At weak signals, you're of course dominated by statistical error, and you don't expect to reconstruct precisely the right ejected signal strength. Now, on the bottom, we also have this question of okay, good. So in the middle plot, we saw we could set safe limits. The bottom plot, what we're seeing is that not only do we set safe limits, but we're actually discovering something. So what I'm showing you is our detection test statistics. So you can think of this like a chi-squared quantity, or a delta chi-squared quantity rather. And as you ramp up the injected signal strength, the detection significance increases until it passes our detection threshold of t equal to 100. So this is great. We have a framework that can both set safe limits and just discover signals that are present in the data, and that's what we needed. Cool. So if you apply this analysis procedure to all of the coarse channels that we have in our data set between 4 and 8 gigahertz, this is what the flux density limits that we extract look like. So in black, I'm showing you our fiducial limits that also include some assessment of systematics that may be present in the data. And you should compare that to this dashed gray line, which is the radiometer equation expected sensitivity for the observations that we were using. So this is really nice. We're tens of percent off of the radiometer equation floor. And that's kind of the best you can hope for because, of course, radio observations are being done on the ground. And although they are done in radio quiet environments, there are plenty of sources of terrestrial backgrounds, along with sort of the typical instrumental problems that you might run into with such high precision measurements. Okay, so we have flux density limits, and thanks to the spectra that Sam's able to generate, we can translate those flux density limits into limits on the Axion photon coupling. So Sam talked about a conservative model and an optimistic model, one where the B fields decay and one where they're just frozen in at birth. And the funny thing here is actually that there's not that much difference in terms of the strengths of the limits that you would set from your conservative model versus your optimistic model. And this largely has to do with the role of very large conversion probabilities modifying the flux density that's emitted by neutron stars. So even though these optimistic neutron stars, they might be expected to give very large conversion probabilities, they get hit to a similar degree by that effect, and ultimately have very similar limits as in the decaying B field scenario. I should also comment that there's this thick line, which is sort of the limit that we're presenting, but there are also some bands. And those bands are just saying, we got these limits by doing some population synthesis. So we modeled the population of neutron stars. We found the best one in terms of detection, and we set limits based on that best one. But of course, there's variance in what is the best neutron star from one population sample to the other. So these bands are just showing you, like, if you got really lucky and had a great neutron star population and that it gave you one really, really bright neutron star, your limits could be a little bit stronger. If you got very unlucky and your population didn't have any very good neutron stars, your limits could be a little bit worse. Of course, all of this is necessary because we don't know, we haven't identified every single one of the neutron stars in the galactic center, along with these parameters that Sam needs to make flux density spectra. We have to model them. Cool. And so we set limits, and the second reasonable question to ask is, did we find anything? And I should just say that the data analysis was a little bit messy. So if we, that's why we had quite a few observational controls along with this flexible Gaussian process modeling implemented. So I'm showing you in the top plot what the survival function for detection test statistics looks like. So when we just opened up the data, applied our analysis, and said, what did we get? We got detection test statistics that were as large as like 10,000, so 100 sigma. And I'm not here telling you that we've discovered Axion dark matter because we use many of the analysis controls that we had available to us to beat down some of those large excesses. So one example of a control we implemented was, if you see a large excess in the galactic center, but you also see the same excess when you point at a flux calibrator, that probably wasn't an Axion. That was some instrumental effect or some reason that some terrestrial background, something that you shouldn't think too seriously about. And of course, these survival functions are always nice because they give us sort of a way to make a posterior assessment of how well did we actually do, because we looked at 44,000 different frequency bins where a signal could appear. We only expect to find one Axion, which means really we only expect to see one very large excess. And at essentially everywhere else, the data should be tracking sort of the expected distribution for test statistics. And that's indeed what we see after we've implemented all of our analysis controls. So I think this is good. We have Axion limits. They are a factor of a few stronger than CAS. So we get down to about 10 to the minus 11. And we don't have any excesses, which means we can keep looking and hopefully find something someday. So I should just maybe provide an outlook, which is that I think that there's a lot to be excited about in terms of looking for these conversion signals. Well, when SKA comes online, it's going to be a really incredible telescope for these searches. So what I'm showing you on the right is, let's say we take our optimistic population and we do the exact same analysis that we did with GBT, we just use SKA data instead. So basically, we have a better gain. With that simple, just by changing instruments, doing nothing at the level of the analysis, we expect to be able to push these limits down to about 10 to the minus 13 inverse GeV, which would be very cool. But there's also a lot of other handles on the data that we haven't made use of in this GBT analysis that could, in principle, give you improved sensitivity. So of course, these neutron stars, these are going to look like point sources, point-like spectral line emission. So in radio interferometer arrays, you can of course leverage that spatial information to say, oh, is it point-like, or if it's not point-like, that's inconsistent with our expectation of how the signal should arise, and that's a fake excess, and we can indeed set a stronger limit. Along with that, there's a whole population of these neutron stars, and we haven't looked at the time variation. So you might expect these neutron stars to be pulsing in terms of their conversion signal as they rotate. Along with that, since we only looked at the constraint that would be set by the brightest individual neutron star in our sample, a more optimal analysis, which is something that we're working on now, would make use of all of the neutron stars that we expect to appear with a particular spectral morphology that we can extract, again, from these ray tracing simulations. So I think there's a lot to be excited about. In the future, these limits will just get better with better radio telescopes, and there are a lot of ways that we can improve an analysis to hopefully push down very close to, if not at, the QCD Axion line. All right, thanks, and happy to take any questions.
Thank you very much for the very nice talk. And I would say that we'll take like 2 questions, and then we can continue like leaving the Zoom room open. So is there any question?
I have a question, if I can start with. So this is maybe a very dumb question because I don't remember the numbers. So you're showing number like from like 10 microelectron volt, right? 20 microelectron volt, and you don't seem to have any absorption like feature. Like I think about free absorption for electron density, like especially for low latitude in the galactic center may be present. So I was wondering if it's just like at lower frequency, and so we don't see any absorption, and that also probably will depend, because I don't remember if it was like 200 megahertz, 300 megahertz, something like that. And also if that could be affected if, for example, instead of having some homogeneous density distribution like the one that we expect in the galactic center, maybe we have larger densities around the pulsar itself, and so this would cause some absorption, and so some reduction of the signal that you don't perceive, but maybe was coming out from the neutron star.
Yeah, no, cool. So I think at these high frequencies at these frequencies, I don't believe that emission after you've gotten sufficiently far away from the neutron star, but like I guess you're encountering some astrophysical medium. I don't think that is supposed to be a particularly important source of signal attenuation, but that would be something I think worth looking at. As far as what happens near the pulsar, maybe that's a better question.
No, near the pulsar, I agree. I meant more about what I meant by more. I meant just about the interstellar medium outside the pulsar. Say after the magnetosphere is down, right? So the magnetic field is down, it goes down. Yeah. So probably the frequency is still too large, but I just don't remember the number for free absorption.
Yeah. I don't remember the number off the top of my head, but I'm happy to look it up for you. Yeah.
There could be some sort of scattering screens in between the pulsar and the source. Like, for example, this is what we see in Crab, like when there is like some scintillation kind of events.
Right, exactly. I would think about similar stuff, yeah.
This doesn't attenuate the signal, but it can sort of caustic it in some sort of, brighter signal, apparently.
Mm-hmm.
Yeah, so I think that, you might worry about like, so for FRBs, right, you worry about the dispersion measure and how long did the light take to propagate to you as a function of its frequency. But of course, that's relevant because FRBs are like, have relative width of like 50%. 30%. Whereas here we're looking at ultra narrow signals where the signal should all still arrive at the same time. And even if it didn't, we're not making use of timing data anyway.
Mm-hmm. Andre, to answer your original question, we're about an order of magnitude above the point at which the free emission along the disk is relevant.
Thanks, Sam.
And that, of course, depends on the on order of magnitude in frequency that goes like square. So you would require like few order of magnitude in density, right? In order to right. Yeah. Okay. Okay. Thanks.
Okay. Let's see if there is any further question or. Okay, so I will ask MITP to stop recording.
Are they there? Sure. So did the recording stopped or not yet? No.